Hello. In the previous videos, we study Riemann sum and we use Riemann sum to approximate the area of some region enclosed by the graph of a function on some interval. Today, we discuss about Riemann sum for any function, any continuous function, let's say this, and we define definite integral using Riemann sum. Okay, so on your screen you can see the Riemann sum looks like Rn equal to sum of fxi star times delta xi, right? And when we study Riemann sum, we say all delta xi have the same width, right? But actually, in general, yeah, you don't have to make that. That means if you have some interval a and b, you may just break, this interval into n subintervals, and each, all subintervals should not have the same width. Does that make sense? But if you have the same width in here, everything would be easier for you to evaluate this sum. So I might write, yeah, you have x0 in here, and you have x1 in here, you might have x2 write this, and so on. You have xn minus 1, and that is your xn. And each time, you have delta xi is equal to, that is just xi minus 1. Okay, just like this is, you have delta x1, you have x1 minus x0, and here you have delta x2, right, and so on, and here you have delta xn. And what is xi star? Xi star is some point in the I interval, right? In that interval, for example, in the first interval you pick xi star, x1 star. Does that make sense? In the second one you might pick x2 star, and so on, because we have n subintervals, so you have n xi star, and then you sum them up, you get a Riemann sum. Does that make sense? So when xi star are left endpoints, you have Riemann sums with left endpoints, right? And if xi star are right endpoints, so you have the Riemann sum formula using right endpoints. That's it. So that is general definition of the Riemann sum. Okay, then as we have seen in the last video, we need to consider the limit, right? Okay, now you consider the limit of Rn. But the limit of what? When n approach infinity, is it enough or not? Look at this. The limit of sum I from 1 to n f of xi star delta xi. But I just wonder, is it enough or not? Because last time we considered subintervals of the same width. So when you tend n to infinity, if the limit exists and equal to a finite number, you get the exact area of the region. But in this situation, we don't require that our subintervals have the same width. So maybe we need something more than just n approaches infinity. Here's a counterexample. Suppose that you have some function f of x, and that function is above the x-axis, okay? And you want to find the area of the region enclosed by the graph of this function on some a and b, and you want to use a Riemann sum. Okay, so look at this. I will choose the following partition. That is my x0, that is my x1, the midpoint of a and b, and x2 is the midpoint of x1 and b. x3 is the midpoint of x2 and x and nb, and so on. So each time I just choose the midpoint, midpoint, midpoint. Okay, even on the first interval, look at this. On the first interval, you use left endpoint or you use right endpoint, you still have an arrow. Does that make sense? An arrow may be right here or might be right here. That means this partition will not help you to get the exact area of the region. Does that make sense? So you see, in this case, you may get a sequence of points, right, or midpoints. In this case, yeah, you may get n approaches infinity, but that is something different than the exact area. So you need something else. Let me remind you about that, right? We have b minus a over n, and we know that this approach 0 because we need this, right? We need this approach 0 in order to avoid the error. And that is equivalent to the case that when the number of subintervals approach infinity. But in this case, delta x, the width is not the same. So probably we need to choose the maximum of width, right? Or the maximum width in each partition. So the maximum width among, I can write in here delta x, among delta x. Does that make sense? So if the maximum of width approaches 0, then this is equivalent to the case, n approaches infinity. Or at least you may say, yeah, when you consider some partitions, right, such that the maximum approaches 0, then the limit of n approach infinity for such partition will be the limit of Riemann sum when the maximum width approaches 0. And that will give you the exact area. So in this situation, we need to introduce the norm of the partition. Okay, so we need to introduce the norm of a partition. So that is the maximum width of subintervals. Okay, so that is the norm of partition. And you need to consider the limit. Let's say that's denoted by norm of delta x. Okay, so you need to consider the limit of Riemann sum when the norm approaches 0. Or let's say that is a Riemann sum from 1 to n f of xi star delta xi, and then here you have norm delta x approaches 0. So now I think we are ready to define definite integrals of functions. Suppose that the function f is defined on a and b, and the limit of Riemann sums over partitions delta is x. Then f is said to be integrable on ab, and the limit is denoted by this symbol, which is called the definite integrals of f on a and b, right? So a and b are integration limits, okay, and the function f is integrand function. All right, so if you look at this definition, you would see that actually indefinite integral and definite integrals are defined differently. Because definite integral is a number. You see that? Indefinite integral is a family of functions. So, they are quite different. But in the future, we'll see actually they are related. We can evaluate definite integrals using indefinite integrals. Okay, now let's consider some examples. The first example, let's evaluate the following integral from negative 2 to 1 to x dx. So in this case, our function is 2x, and the interval a and b is negative 2 and 1, right? We did a lot of problems like this, in the last video. So we need to make the Riemann sum, in this case, yeah, it turns out that you just need to consider the case when subintervals have the same width. Does that make sense? And then, if the limit is x, so that is your definite integral. So if you write Riemann sum, you need to make some partition, right? Partition, and in that partition, you have x0 equal to negative 2, xi equal to I x0 plus I times delta x, where delta x is b minus a over n, right? That is 1 minus negative 2 over n equal to 3 over n. So from here, you can find all xi. Okay, let's say x0 is negative 2, xi is negative 2 plus 3 over n. Okay, and xn is equal to 1. Now you can write your Riemann sum using left or right endpoints, whatever you want. Okay, so I would like to use left endpoint. So if we work with left endpoint, so we need to start from the very first point, right? Which is x0, and then we finish at the xn minus 1. Does that make sense? Here you have, xn, which is 1. So I write the Riemann sum Rn. That is sum I runs from 0 to n minus 1 because we use left endpoints. And here you have f of xi times delta x, because all subintervals have the same width. The function is 2x. We have xi right here. So that is sum I from 0 to n minus 1. F of xi is 2 xi, right? Times delta x is 3 over n. Then I can take 3 over n out. Even I can take 2 out, right? So I have 6 over n, let's say this. And inside I have I from 0 to n minus 1. Xi is negative 2 plus 3 over n, right? So I can break this into two sums. The first one is negative 2, I from 0 to n minus 1. And the second one is plus 3 as 3n. Yeah, actually you can write 3n. I think I do something wrong in here. Here I think I mix I. Sorry for this. So I have I in here. And this is 3 over n. I can take 3 over n out, right? And I run from 0 to n minus 1. So you have sum of n minus 1 integers. All right, so from here you can see, yeah, actually that is 6 over n. And this is just equal to times negative 2, right? Times n. Does that make sense? Okay, let me write step by step. So I have negative 2, I from 0 to n minus 1. Here I have 1. And then plus 3 over n. So you have i's run from 0 to n minus 1. But, that is nothing but, I from 1 to n minus 1. Because I equal to 0, it's not counted, right? So I can write here just I from 1 to n minus 1. Here we have I. Now we have 6 over n, negative 2. Here you have n ones, right? Because the index I runs from 0 to n minus 1. You have n terms over there. So that means you have n in here. Plus 3 over n. Here you have sum of the first n minus 1, a natural number. So, I have n minus 1 times n minus 2 over 2. We have such formula. Okay. Then I might simplify this. Let's for this out. Okay. So I have negative 12 plus 6 with 3 is 18. 18 divided by 2 is 9. So I write 9 in here, okay? I have n minus 1, n minus 2 over n squared. Because you have one n in here and another n right here. Now, in order to find definite integral, we need to consider the limit of this Riemann sum, right? So I can write in here, definite integral from negative 2 to 1 2x dx is equal to the limit of negative 12 plus 9 times n minus 1, n minus 2 over n squared. N approaches infinity. Okay, and we just discussed about this, right? This condition is, equivalent to the case that delta x, the norm of this partition, approaches 0. Okay, so that is negative 12 plus 9 limit of n minus 1 times n minus 2 over n squared, n approaches infinity. And in this case, we can use similarity. We have negative 12 plus 9, limit of n times n over n squared, n approaches infinity. So you get negative 12 plus 9, because this is just 1, right? And that is negative 3. So that is definitely integral from negative 2 to 1 of 2x dx. You see, that is not bad at all, right? So basically, the instruction we use in this case is similar to the case when we studied the area problem. And of course, if the function is non-negative, right? Non-negative, that means, the graph of the function on this interval is above the x-axis. Let's write it down. That means, the graph of f of x is above the x-axis. Then the area problem can be solved using definite integral. Look at this. So you have the following picture, right? That is A, that is B, and this is the area problem, right? We need to find the area of this region. So the area is nothing but the definite integral from A to B. Okay. Now let's sketch the region corresponding to each definite integral and then evaluate each integral. So the first integral is from 1 to 3, the function is 4. So in this case, the integral function f of x is a constant, right? So if you draw that, you have the following picture. This is your x, o, y, here is 1, here is 3. Okay, let's say 3 is right here, okay? So the interval is from 1 to 3, and your function is 4. Okay, let's say this is 4. So you have this right here. I don't know what happened with the function outside of this interval, but on 1, 3, the function is just 4. So, the function is positive, right? And the graph is above the x-axis. That means the area of this region is just definite integral from 1 to 3. Then you can see that actually the area is equal to 3 minus 1 times 4, which is 8. Does that make sense? All right. The second integral, you have function f of x equal to x plus 2. And the interval is, 0, 3. Look at this. So let me graph the function. You have y equal to x, and then you move that. You shift it on 2 units, right? Let's say this is 2. This is negative 2. So that is your function. Okay. So this is the graph of y equal to x plus 2. And you consider the case when x from 0 to 3. So you have this interval, right? And you can see on this interval, the graph of the function is above the x-axis. Means the function is positive, right? So the area of the region, or in this case we have trapezoid, is the definite integral. So I can see the area of this guy equal to, you need to plug, right, 3 into the function, you get 5 in here. That is the function value. So that is 1/2 of the height, which is 3 minus 0 times f of 0 plus f of 3, right? So overall that is equal to 1/2 times 3. F of 0 is 2 plus 3 is 5. So you get, 21 over 2. And that is our definite integral. I write like that is 21 over 2. Does that make sense? Now let's move to the last example. So the integrand function in this case, f of x equal to square root of 4 minus x squared. And if you put this as y, then you square both sides, you get 4 minus x squared equal to y squared. Or x squared plus y squared equal to 4. So this is nothing but the equation of the circle, right? Centered at the origin and the radius is 2. So I can draw this circle, center at the origin, radius equal to 2 in here. Alright, that is my circle. Not beautiful, but I hope that is okay. And you consider this definite integral from -2 to 2. -2 is right here and 2 is right here. Okay, and you have square root of 4 minus x squared. So that means you just consider a half of that circle, and that half is above the x-axis. Does that make sense? So basically, that definite integral is the area of this region. So that is just a half of the area of the circle. Right? So I have definite integral from -2 to 2. 4 minus x squared dx is equal to 1/2 pi r squared when r is 2. So you have 2 pi. You see, that is, how we can use definite integral to find area of the region. And actually in these problems, we use well-known areas, right? We use well-known, figures to evaluate definite integrals. Okay, so again, right, definite integrals are defined not only for non-negative functions. So the only common in this situation between the area problem and definite integrals is you use Riemann sums. And since when you use Riemann sum, everything is additive. So that's why when you evaluate definite integrals, let's say you evaluate integral on A and C, right? But B is some point in AC. So it means you have the following picture, like you have here's A, here's C, and here's your B, right? B is somewhere in here. So you might break, the integral into two integrals, right? In that case, integral from A to C of fx dx equal to integral from here should be A, from A to B f of x dx plus integral from B to C f of x dx. Agree? That is very straightforward consequence of the additivity of Riemann sums. And the second property of definite integral is integral from A to A fx dx is 0. So what does it mean? That means you integrate at only one point. So you can imagine, right? If you have only one point right here, A, and suppose that your function is positive, right, at A. So what happened? Look at this. You have this, right? You have x in here, and then you take the limit x when x approaches A. That means this area, the area of this region, is just close to 0. Does that make sense? Because the function is continuous, right? So that's why you have definite integrals from A to A. It's just 0. Or you can see that using the Riemann sum, because delta x is 0. All right. The third property. If f is integrable on A and B, then integral from A to B f of x dx equal to negative integral from b to a f of x dx. Let's see. So when you switch integration limits, the integral just change the sign. This of course can be proved again using the Riemann sum. Because if you do partition, right, from A to B, right, if you want to go back to in the other direction, so you just add negative to each delta xi. Does that make sense? That is one case. But when you consider definite integrals as the area, so this is interesting observation. So that is, suppose this is your function, right? So the integral from A to B, that is the area of this region. So what does mean integral from B to A? So you go this way. So here you have negative B to A of f of x dx. Does that make sense? But again, right, just say it depends on the direction when you integrate. You integrate from B to A, from A to B means in this direction, right? But when you integrate in another direction, so you just change the sign. Agree? Let's consider the following example. You have integral from -1 to 1 absolute of x dx. So in this case, you have absolute, right? What is absolute? Absolute is equal to x if x bigger than or equal to 0, or negative x if x less than 0. And the graph of this function looks like this. Right? This is y equal to x, and this is y equal to negative x. So if you consider the interval from -1 to 1, you have the following picture. So actually you have two regions in here. The first region is corresponding to the interval -1 to 0. The second one is for 0, 1. So you cannot evaluate this definite integral directly. You need to remove the absolute first, right? So you might rewrite, this is equal to integral from -1 to 0, and in that situation you have negative x dx, because x is less than 0, the absolute is equal to negative x, you see. And then from 0 to 1, the function is just x dx. Does that make sense? But if you look at the picture, right, so these two integrals should be equal, and equal to the area of this triangle and the area of this triangle. Two triangles are equal, so the area should be the same. Does that make sense? And from here you get 2 times integral from 0 to 1 x dx. And since the area of this is just 1/2, so 2 times is just 1. Okay. In general, if you have two integrable functions f and g on some interval a and b, so you have the following one. Integral from a to b of f x plus minus gx equal to sum of difference of two integrals. And if you have some constant c in here, you can take the constant out of the integral. And again, all this just comes from the definition of definite integrals. Okay, so we also have the following property. If your function f of x is greater than or equal to 0 on a and b, then definite integral from a to b of f of x dx is greater than or equal to 0. That is obvious because, in that case, definite integral is the area of the region enclosed by the graph of the function on AB. And if you have f of x less than or equal to g of x on AB, then the definite integral from a to b of f less than or equal to integral from AB of g dx. This is very straightforward consequence of this property. You just subtract, right? You just consider the case when g minus f. Okay, and then we know the definite integral of g minus f is non-negative, and from additivity of integration you can see this property. In order to finish this video, let's consider one more example. Okay, and then I think we are good for today. Let's evaluate the following integral. If we know that definite integral from 1 to 3x squared is 26 over 3, integral of x from 1 to 3 is 4, and integral from 1 to 3, I think from -1 to 3, sorry, of 1 dx is 2. No, I think we have just 1 in here, sorry. So it is pretty easy because we just use additivity of definite integral. So you have this dx equal to 1 3. In here you can take minus here x squared dx, right? Then plus 4 times of integral from 1 to 3 x dx, and minus 3 from 1 to 3 dx. And you can see that as given we have negative 26 over 3 plus 4 times 4 and minus 3 times 2, and you just simplify this, you get 4/3. Of course, this function is pretty easy. I tell you this, you can use Riemann sum to evaluate that definite integral. And I think in that case we need to use some formulas, like sum of the first n natural numbers or sum of squares of the first n natural numbers. So I hope you can make that yourself. Okay, so in my opinion, this video is pretty easy, in the sense that we only need to understand how the definite integral can be defined using Riemann sums. Other than that, the technique we use in this video is similar to the one we learned from the previous video with the Riemann sum. Okay, but in the next video we'll learn more about this, and we'll learn more integration techniques, so that will be more complicated. Okay, thank you for watching, and if you have any questions, please feel free to let me know. Okay, bye.